the common ion functions to reduce extent of reaction. Period. So, if you have a common ion and you add a weak acid or a weak base, the amount of ionization from the weak acid or weak base will be less than it would be in pure water. That's the point. So how do we deal with this? Okay, say we're given a 0.10 molar acetic acid in aqueous media that will be in the aqueous media is added into a 0.01 molar sodium acetate aqueous solution. Okay. What is the hydronium ion concentration and acetate ion concentrations to make that comparison? And B, determine percent ionization in common ion solution and in pure water. The Ka, of course, for acetic acid is 1.8 times 10 to the minus 5. That's given in the problem. So we're given a 0.10 molar acetic acid solution and a 0.01 molar acetate, sodium acetate, but the common ion's the acetate ion. So I'm just going to focus on that right here. Now, when calculating the hydronium ion for a weak acid in pure water, you can use the square root formula. Yes? You know that. In the common ion system, you cannot. The reason is you've already got part of the ion concentrations present. So in setting up the ice table, you'll see this. Initial, change at equilibrium. So what we're going to do is we're going to start with this 0.1 molar in the initial step before anything happens. And in the past, you put 0 and 0 on the right. However, that's not the case in this problem. We already have a 0.01 molar in the acetate ion. What we don't have is the hydronium ion delivered into solution from the 0.1 solution going into the solution in the presence of the common ion. So that's why you can't use the square root formula, because you won't have the x squared in the Ka expression. Part of that x is the 0.01. It's already present. Now from here to the equilibrium, you decrease by x, increase by x, and increase by x. And it's 0.10 minus x, and you can drop the x, and it's 0.10 molar, and x, 0.01 plus X, which you can drop the X. The X makes very little contribution. It'll be in the 10 to the minus 5 range kind of thing. And so 10 to the minus 5 plus 10 to the minus 2, you don't see a change. So this becomes 0.1 molar. So there's your equilibrium row that you must substitute into your Ka expression. And so that would be hydronium ion, acetate ion, divided by the acetic acid concentration at equilibrium. And so that's X times 0.01. So you can't go X times X here. And so that is divided by 0.10, and all of that comes out, oops, no, not yet. I haven't solved for X yet. Those are supposed to be in molar concentrations anyway. Okay, I'm going to lose some of my problem here. Right here, oh, and that's 1.8 times 10 to the minus 5. So this is what you want to solve for X. Now, as you see, X is the, excuse me, wrong one. X is the hydronium ion, is what we want to calculate in this one. So solving for X, that would be 0.10 times the K value, 0.8 times 10 to the minus 5, over 0.01. Now everything comes out in moles per liter. That's 1.8 times 10 to the minus 4 molar. Now, in hydronium ions, like that. Well, pure water ionization gives a 0.0013 molar solution. So when you compare these two, you see about a 10 times drop in the amount of ionization between the pure water and the common ion effect up here. Now, when you go to the concentrations of the acetate ion, it's still 0.01 because the 1 times 10 to the minus 4 added to 0.01 doesn't make any difference. So I wanted to show you that. Most problems won't even ask you about the counter ion in the ionization at all. Okay. In essence, calculate the percent ionization in the presence of the common ion. Well, we've got the hydronium ion from the previous problem was 1.8 times 10 to the minus 4 here. So how much, in calculating a percentage of the fraction, is the amount of hydrogen delivered from the original concentration of the HOAC. So that's the part over total times 100. So the percent ionization is the delivery of the hydronium ion, which is 1.8 times 10 to the minus 4 divided by 0.10 times 100%. And times 0.18% ionized. That's in the presence of common ion. Well, a moment ago I told you that the hydronium ion concentration in pure water ionization is 0.0013 molar. And if we use the same concentration to make a comparison, then the percent ionization in pure water would be 0.0013 over 0.10 times 100%, and that's 1.3% ionized. So when you compare the two, you see a significant drop in the overall ionization. If you calculate this, 1.8 times 10 to the minus 5 times 0.10, you will get a 0.0013 molar hydronium ion concentration. But that's pure water. That's what I'm emphasizing. So what I'm trying to do here is, I've done it so much, I just knew what that concentration would be. But yeah, good question. If it doesn't click, then yeah, what I'm showing you is pure water against a common ion effect. That's all. Does that help?
Yes.
Okay. Okay. Here's what I'm given. A 0.75 molar hydrofluoric acid solution. Okay, and common ion is equal to 0.12 HCl in that. Now, what I want you to do is calculate percent ionization in pure water. I'll look up the Ka value. And B, calculate percent ionization in 0.12 molar HCl. So you can see the change in degree of ionization. Okay, Ka for this. Okay. So what it's done is you've ionized partially, but you get equal amounts over here in pure water. So how do you get in pure water the hydronium ion concentration? What do you use? What formula? The square root formula. That's right. You don't have to go through the ice table setup. Is everybody clear on this? So you look at it and you ask yourself, are you in pure water or not? If you're in pure water, just go use the square root formula. So that'd be the square root of the Ka value for the acid, and since we're using the hydrofluoric, it would be HF, and so that would be 6.3 times 10 to the minus 4 times 0.75 molar. I get 0.022 molar in H plus, and as a matter of fact, and the fluoride ion. So if I'm going to calculate the percent ionization out of this, it's the the hydronium ion over hydrofluoric acid times 100. So that would be 0.022 for the amount of acid hydrogen delivered over 0.75 times 100%. So I'm looking at a 2.9% ionization in pure water. Okay. Now, if we put this into a 0.1 molar common ion solution of HCl, where the common ion is the hydronium. Now, I could add, change the problem up and go a 0.12 of, say, a sodium fluoride, where the fluoride would be the common ion. So be sensitive to that in your problem structure. So for this second part, you already have some hydronium ion present, and that's given to be 0.12 molar. So you come in here 1,2 molar, and you haven't delivered the fluoride. It's the amount of fluoride in this one that defines the degree of ionization. And so that's what you were looking for in your ice table. And you started with a 0.75 molar solution. And then you're changing C and C at equilibrium. Minus X plus X plus X. So whatever we get for X is divided by 0.75 and times 100. Of course, you can drop the X. If it's decreasing ionization, you can certainly drop it in the common ion. You can drop it in the pure water. And, of course, X. So now we want to apply this to the equilibrium expression. And solve for the fluoride concentration. Of course, that would be 6.3 times 10 to the minus 4 to equal 0.12x over 0.75. Solving for x, we get 0.75 times 6.3 times 10 to the minus 4 over 0.12, and that would be the fluoride. Let me move this on up here. So I've got a 0.0040 molar solution in the fluoride. Right there. So the percent ionization now is dependent on, see, that's the one that tells us how much was delivered. We went from 0 to X. We can't use the hydrogen in this case. It depends on the one that's delivering, that starts at 0 and then delivers a certain amount. And then you calculate the percent ionization. And so that's a 0.53% ionized. In pure water, it was 2.9. So the common ion effect certainly knocks the degree of ionization way down. Now, in the nature of the common ion effect is the foundation for what we call buffer solutions. And so that's the next topic that we were getting into. So let's go ahead and take a break now, and I'll start at 12:30.